Hello, everyone, and a warm welcome to the introductory module on organic chemistry. If you have some experience with cooking, you know how a variety of spices can enhance food flavor, often transforming a bland dish into a culinary delight. The characteristic flavor, aroma, and color of each spice come from various organic compounds. For instance, your morning cinnamon rolls get their flavor from cinnamaldehyde. Curcumin gives turmeric its bright yellow color, and cayenne pepper and other hot peppers derive their heat from capsaicin. Except for a few inorganic salts and water, nearly everything we consume or apply to our bodies consists of organic compounds. This includes food, medicine, cosmetics, and clothing, to name a few. Organic fuels are essential for warming our homes, cooking our meals, and powering our vehicles. As a result, major industries focus on producing organic compounds, including plastics, pharmaceuticals, and insecticides. All organic compounds contain carbon, which is typically bonded to one or more other carbon atoms, hydrogen, and often other elements. The same chemical principles you have learned so far apply to both inorganic and organic compounds, and their behavior can be understood by examining the properties of their elements. In this module, we will briefly survey various classes of organic compounds, examining their properties and reactions. We will start with hydrocarbons, which contain only carbon and hydrogen atoms. Our discussion will include hydrocarbons called alkanes, which contain only single bonds. I will introduce you to the principles of structural drawings of organic molecules, and we will have a short discussion on isomers, compounds with identical compositions but different molecular structures. Next, we will explore hydrocarbons with one or more double bonds between carbon atoms, called alkenes, and those with one or more triple bonds, called alkynes. In the lecture describing alkenes, you will see how our vision works at the molecular level. I will then introduce you to aromatic hydrocarbons, which have at least one planar ring with delocalized electrons. Finally, we will discuss functional groups found in organic molecules, which play a central role in the function and chemical behavior of many organic compounds. Although there is nothing mystical about organic molecules, their indispensable role in biology and industry leads many to wonder if carbon is somehow special. Of course, each element has specific properties, but the atomic properties of carbon provide it with bonding capabilities beyond those of any other element. This exceptional behavior leads to two key characteristics of organic molecules: structural complexity and chemical diversity. You may have noticed that organic molecules often have more complex structures than inorganic molecules. A quick review of carbon's atomic properties and bonding behavior explains why. You may recall from the introductory module of this course that carbon has 4 valence electrons. It is ideally positioned between metals and nonmetals in the periodic table, making the complete loss of electrons energetically unfavorable. As a result, carbon does not form purely ionic compounds. On the other hand, being centrally located in period 2, carbon has an electronegativity that is midway between that of the most metallic element, lithium, and the most reactive nonmetal, fluorine. Consequently, carbon forms covalent bonds of varying polarity with many elements across the periodic table. The number and strength of carbon's bonds lead to its ability to undergo catenation, which is the ability to bond to one or more other carbon atoms, resulting in a multitude of chemically and thermally stable linear, branched, and cyclic compounds. Although silicon and several other elements also exhibit catenation, none form chains as stable as carbon's. Carbon has 4 valence electrons and forms 4 bonds in virtually all its compounds. These 4 bonds point in 4 distinct directions. In addition, carbon's small size allows it to approach other atoms closely, resulting in relatively short and strong bonds. The carbon-carbon bond is short enough to allow the formation of multiple bonds, which restricts the rotation of attached groups, leading to additional structures and stereoisomers, which we will discuss in the lecture on alkenes. In addition to their complex structures, organic compounds are remarkable for their vast number and diverse chemical behavior. Several million organic compounds are known, and thousands more are discovered or synthesized each year. This diversity is based on the atomic behavior of carbon and arises from three interrelated factors, including the ability of carbon to bind with heteroatoms, differences in the reactivity of organic compounds, and the presence of functional groups. Many organic compounds contain heteroatoms, atoms other than carbon or hydrogen. The most common heteroatoms are nitrogen and oxygen, but sulfur, phosphorus, and the halogens are also frequently found in organic molecules. For instance, in this figure, you can see 23 possible molecular structures formed by various arrangements of 4 carbon atoms, a single oxygen atom, and a necessary number of hydrogen atoms to fulfill the octet rule. Please note that carbon and oxygen atoms can be either singly or doubly bonded. Finally, a central feature of most organic molecules is the presence of a functional group, which is a specific combination of bonded atoms that reacts in a characteristic way, regardless of the molecule it is part of. In nearly all cases, organic reactions occur at the functional group. Functional groups include carbon-carbon multiple bonds, as well as various combinations of carbon heteroatom bonds, each with its own pattern of reactivity, which we will discuss in a separate lecture. To sum it up, in this lecture, you have seen that carbon's small size, intermediate electronegativity for valence electrons, and ability to form multiple bonds contribute to the structural complexity of organic compounds. These factors lead to carbon's ability to catenate, which creates chains, branches, and rings of carbon atoms. The small size of carbon leads to strong, chemically resistant bonds that point in up to 4 different directions from each carbon atom. You have also seen that carbon's ability to bond with many other elements, especially oxygen and nitrogen, creates polar, reactive bonds, which is one of the key reasons for the chemical diversity of organic compounds. Most organic compounds contain functional groups, which are specific combinations of bonded atoms that react in characteristic ways. We will have a detailed discussion of this topic later. In the next lecture, you will be introduced to alkanes. We will explore the concept of isomerism, and you will learn how to draw and interpret organic structures. Thank you for your attention. Hello, everyone, and welcome back to the lecture series covering the basic principles of organic chemistry. If we draw an analogy between an organic molecule and an animal's anatomy, we can compare the carbon-carbon bonds to the skeleton of an organic compound. The longest continuous chain of carbon atoms can be considered the backbone of a given molecule, while any branches represent the limbs. In organic compounds, covering the skeleton with a skin is achieved by placing the appropriate number of hydrogen atoms to fulfill the octet rule. Functional groups can also protrude at specific locations, acting like chemical hands ready to grasp an incoming reactant. In this section, we will discuss hydrocarbons, the simplest class of organic compounds, which contain only hydrogen and carbon atoms. We will begin by examining the possible bonding arrangements in simple carbon skeletons, without multiple bonds or rings. So, carbon chains with 1, 2, or 3 atoms can only be arranged in a single way. Whether 3 carbon atoms are drawn in a straight line or with a bend, the arrangement remains the same. For carbon atoms, however, can be arranged in 2 ways: as a straight 4-carbon chain or as a 3-carbon chain with a 1-carbon branch attached to the central atom. If we represent these chains using a ball and stick model, while considering that carbon atoms in saturated systems are tetrahedral, the differences between these arrangements become very clear. Notice that if the branch is added to either end of the 3-carbon chain, it simply forms a bend in a 4-carbon chain and does not create a different arrangement. Similarly, if the branch points downward instead of upward, it still represents the same arrangement since single bonded groups can freely rotate around carbon-carbon bonds. As the total number of carbon atoms increases, the number of possible arrangements increases as well. For instance, 5 carbon atoms joined by single bonds can be arranged in 3 different ways. 6 carbon atoms in 5 ways, 7 carbon atoms in 9 ways, 10 carbon atoms in 75 ways, and 20 carbon atoms in more than 300,000 ways. If multiple bonds and rings are included, the number of possible arrangements increases even further. For example, adding just 1 carbon-carbon double bond to a 5-carbon skeleton creates 5 additional arrangements, and introducing a ring results in 5 more. When determining the number of possible skeletons for a given number of carbon atoms, remember that each carbon atom can form 4 single bonds, 2 single bonds and 1 double bond, or 1 single bond and 1 triple bond. Otherwise, the octet rule would be violated. Also, keep in mind that a straight chain and a bent chain of carbon atoms represent the same skeleton. In a single bonded arrangement, a branch pointing downward is equivalent to one pointing upward. However, a double bond restricts rotation, meaning that different groups attached to a double bond can lead to distinct arrangements. Once you have your hydrocarbon skeleton, you can begin placing hydrogen atoms on each carbon, which will eventually lead to fully formed hydrocarbons. In this figure, you can see different scenarios for adding hydrogen atoms to a carbon skeleton without breaking the octet rule. Remember, when drawing the expanded formula of an organic compound, you should always follow the octet rule. Hydrocarbons can be classified into 2 main groups: aliphatic hydrocarbons and aromatic hydrocarbons. Aliphatic hydrocarbons can further be divided into 4 subgroups: alkanes, cycloalkanes, alkenes, and alkynes. In the rest of this module, we will discuss their structural features and physical properties. Later, we will explore their chemical behavior. We should start with hydrocarbons that contain only single bonds. These are called alkanes, and they have the following general features. Alkanes follow the general formula CnH2n plus 2, where n is a positive integer. For example, if n equals 5, the molecular formula of the alkane is C5H12. Alkanes constitute a homologous series, in which each member differs from the next by a CH2 or methylene group. The first 10 members of the straight-chain alkane series are listed in this table. In an alkane, each carbon atom has 4 substituents, making it sp3 hybridized. Since each carbon is bonded to the maximum number of other atoms, alkanes are often referred to as saturated hydrocarbons. You have previously learned how to represent molecules using Lewis structures. Here, we will discuss several additional ways to represent molecules, methods that are particularly useful in the study of organic chemistry, macromolecules, and biochemistry. The representation of organic molecules is especially important because, as you will soon see, the atoms in an organic molecule, unlike those in many inorganic compounds, can be arranged in an enormous variety of ways. A condensed structural formula, or simply a condensed structure, conveys the same information as a structural formula, but in a more compact form. For instance, the molecular formula, structural formula, and condensed structural formula of propanol are shown here. As another example, we can examine octane, a hydrocarbon composed of 8 carbon atoms, and compare its molecular formula, structural formula, and condensed structural formula. Note that in the condensed structural formula, identical adjacent groups of atoms, in this case CH2 groups, are enclosed in parentheses and subscript to indicate their number. In molecules where the carbon atoms do not form a single unbranched chain, branches are indicated using additional parentheses in the condensed structural formula. For example, 2-methylheptane has the same molecular formula as octane, but this time the chain is 1 carbon atom shorter, and one of the hydrogen atoms on the second carbon has been replaced by a CH3 group. commonly called a methyl group. Now, let's have a look at Kekulé structures, which are similar to Lewis structures except that they do not show lone pairs on heteroatoms. For molecules that contain no lone pairs, such as octane, the Lewis and Kekulé structures are identical, as demonstrated below. Please note that most of the structures you have seen so far are Kekulé structures. The Kekulé structures for several familiar organic molecules, such as propanol, ethanol, formaldehyde, and acetic acid, are shown here. In the end, we should examine the most common way of representing molecular formulas, known as bond-line structures. Bond-line structures are especially useful for depicting complex organic molecules. A bond-line structure consists of straight lines representing carbon-carbon bonds. The carbon atoms themselves and their attached hydrogen atoms are not explicitly shown, but it is understood that they are present. The structural formulas and bond-line structures for two saturated hydrocarbons are presented here. Note that the end of each straight line in a bond-line structure corresponds to a carbon atom unless another type of atom is explicitly indicated. Additionally, each carbon atom is assumed to have as many hydrogen atoms as needed to form a total of 4 bonds, ensuring that the octet rule is satisfied. When a molecule contains an element other than carbon or hydrogen, these atoms, called heteroatoms, are explicitly shown in the bond-line structure. Furthermore, while hydrogen atoms attached to carbon are typically not shown, those attached to heteroatoms are included, as illustrated in this reaction scheme, where the alcohol 2-propanol is oxidized to the corresponding ketone, acetone. Although carbon and hydrogen atoms are generally omitted in bond-line structures, they must be shown when they are part of a functional group, as in the case of carboxylic acids. The power of bond-line structures lies in their ability to emphasize functional groups while allowing the hydrocarbon skeleton to fade into the background. As I have already mentioned, this is particularly useful for complex structures, such as natural products or pharmaceuticals, where the function and chemical properties are predominantly dictated by functional groups. In contrast, the hydrocarbon skeleton, being largely inert, primarily serves to support and position these functional groups within the molecule. Alkanes can also be cyclic. A cyclic hydrocarbon contains one or more rings. When a straight-chain alkane forms a ring, 2 hydrogen atoms are lost as the 2 ends of the chain form a carbon-carbon bond. Thus, cycloalkanes have the general formula CnH2n. Cyclic hydrocarbons are often depicted with carbon skeleton formulas, as shown at the top of this figure. Except for 3 carbon rings, cycloalkanes are non-planar, as represented by the ball and stick and space-filling models. This structural feature arises from the tetrahedral shape around each carbon atom and the need to minimize electron repulsions between adjacent hydrogen atoms. You can learn more about this by taking an organic chemistry course. Now, let's review what we have learned about intermolecular forces. Since alkanes are nearly nonpolar, their physical properties and solubility behavior are determined primarily by dispersion forces. A particularly clear example of this effect is observed among unbranched linear alkanes. Accordingly, boiling points increase steadily with chain length. The longer the chain, the greater the molar mass, the greater the intermolecular contact, and the stronger the dispersion forces, resulting in a higher boiling point. For example, pentane, which has 5 carbon atoms, is the smallest linear alkane that exists as a liquid at room temperature. The solubility of alkanes and of all hydrocarbons can also be predicted using the like dissolves like rule. Alkanes are miscible with each other and with other nonpolar solvents, such as benzene, but are nearly insoluble in water. At this point, we should also briefly touch upon the concept of isomerism in organic compounds. Two or more compounds that have the same molecular formula but different properties are called isomers. Those that differ in the arrangement of bonded atoms are known as constitutional or structural isomers. A good example of constitutional isomerism is found in alkanes, which have the same number of carbon and hydrogen atoms but different carbon skeletons. The smallest alkane to exhibit constitutional isomerism has 4 carbon atoms. Its 2 isomers are shown in this figure. The unbranched isomer is called butane, while the branched one is known as 2-methylpropane or isobutane. As the number of carbon atoms increases, the number of possible isomers grows exponentially. For instance, a hydrocarbon with 5 carbon atoms has 3 possible constitutional isomers, which are presented here. The unbranched isomer is called pentane. The one with a methyl branch on the second carbon of a 4-carbon chain is known as 2-methylbutane. The third isomer has 2 methyl branches on the second carbon of a 3-carbon chain and is named 2,2-dimethylpropane. As expected, the physical properties of constitutional isomers depend on the strength of dispersion forces. This relationship is demonstrated by the boiling points listed in the rightmost column of this table. 4-carbon compounds have lower boiling points than 5-carbon compounds because the strength of dispersion forces generally increases with increasing molar mass. Additionally, within each group, the more spherical molecule have a lower boiling point than the more elongated one. This is because a spherical shape allows for less intermolecular contact, resulting in weaker dispersion forces compared to an elongated shape. To sum up, in this lecture, you were introduced to saturated hydrocarbons. We discussed the different ways organic molecules can be represented, constitutional isomerism, and briefly touched upon the relationship between structure and physical properties in hydrocarbons. In the next lecture, you will be introduced to other important families of hydrocarbons, and we will explore the chemistry behind fission. Thank you for your attention. Hello, everyone, and welcome back to the lecture series introducing you to organic chemistry. We have already started examining different families of organic compounds, and in the previous lecture, you learned about saturated hydrocarbons, commonly called alkanes. Unsaturated hydrocarbons contain a double or triple bond between 2 carbon atoms, and they differ greatly from alkanes in many aspects of their chemistry. Understanding the molecular basis of these differences allows us to predict what reactions may occur and enhances our ability to use basic chemicals to synthesize more complex substances, such as macromolecules. These, in turn, may be used to create modern materials that surround us and are applied in fields such as construction, medicine, and technology. We will begin our discussion with alkenes, which are also known as olefins. A hydrocarbon that contains at least 1 carbon-carbon double bond is called an alkene and has the following features. Since 2 hydrogen atoms must be removed to form the double bond, alkenes have the general formula CnH2n. For example, the alkene composed of 5 carbon atoms has the formula C5H10. In olefins, the double-bonded carbon atoms are sp2 hybridized. As the carbon atoms in alkenes are bonded to fewer than a maximum of 4 atoms each, alkenes are considered unsaturated hydrocarbons. There are 2 major structural differences between alkanes and alkenes. All carbon atoms in alkanes have a tetrahedral geometry with bond angles close to 109.5 degrees, whereas the double-bonded carbon atoms in alkenes are trigonal planar with 120-degree bond angles. Another key difference is that the carbon-carbon single bond in alkanes allows free rotation of bonded groups, meaning the atoms in an alkane continually change their relative positions. In contrast, the double bond in an alkene restricts rotation, so the relative positions of the atoms attached to the double bond are fixed. To understand the reasons behind restricted rotation around double bonds, we should consider the atomic orbitals involved in bonding in alkanes and alkenes. In alkanes, all carbon atoms are sp3 hybridized, and bonding occurs exclusively through sigma bonds formed by the frontal overlap of sp3 hybrid orbitals, as demonstrated here for the molecule of ethane. Sigma bonds have cylindrical symmetry, meaning that rotation around a sigma bond does not break it. Now, let's consider the atomic orbitals involved in bonding in alkenes. The carbon atoms in the double bond are sp2 hybridized, allowing them to form 3 sigma bonds with neighboring atoms using the sp2 hybrid orbitals, shown here in purple. sp2 hybridization leaves one unhybridized p orbital on each carbon atom. These unhybridized p orbitals overlap sideways to form a pi bond between the carbon atoms, indicated here in pink. Now, if we examine bonding in butene, we can see why free rotation is prohibited. The pi bond consists of 2 parallel p orbitals. To rotate around the double bond, these orbitals would have to lose their interaction, pass through a state in which they become perpendicular, and then realign. This perpendicular transition state is highly unfavorable because it results in the loss of all the energy gained through pi bonding. This energy loss makes alkenes rigid, preventing rotation around the double bond. The rotational restriction around the carbon-carbon double bond leads to a type of stereoisomerism known as geometric isomerism, also called cis-trans isomerism. In geometric isomers, the orientation of groups around the double bond differs, as demonstrated here for the 2 geometric isomers of 2-butene. Note that in the cis isomer, the CH3 groups are on the same side of the double bond. In general, the cis isomer has the larger portions of the main chain on the same side of the double bond. In the trans isomer, the methyl groups are on opposite sides of the double bond. The trans isomer generally has the larger portions of the main chain on opposite sides of the double bond. Also, note that for a molecule to exhibit geometric isomerism, each carbon atom in the double bond must be bonded to 2 different groups, as is the case for 2-butene. Like structural isomers, geometric isomers have different physical properties due to differences in molecular shape. The cis isomer has a bend in the chain that the trans isomer lacks. This difference notably affects molecular polarity and physical properties, which arise from varying strengths of intermolecular attractions. The trans isomer has no dipole moment because the bond dipole moments cancel each other out. In contrast, the cis isomer has a small dipole moment, as its bond dipole moments do not cancel. This slight molecular polarity results in stronger intermolecular forces and a higher boiling point, as demonstrated on the right side of the figure. Differences in geometric isomers have profound effects in biological systems. For example, the first step in the sequence that allows us to see relies on the different shapes of 2 geometric isomers of a molecule called retinol, which originates from vitamin A. Retinol is an unsaturated hydrocarbon composed of 20 carbon atoms. 15 of these carbons form a chain, while the remaining 5 are part of a ring. The retinol molecule also possesses 5 carbon-carbon double bonds and 5 carbon branches. In our eyes, this molecule is responsible for absorbing light energy and converting it into electrical signals transmitted to the brain. To understand how this process works, we should examine the 2 biologically occurring isomers of retinol shown here. The all-trans isomer has a trans orientation around all 5 double bonds, making it elongated. In contrast, the isomer shown on the left has a cis orientation around the double bond between carbon 11 and carbon 12, causing the molecule to be bent. Interestingly, these isomers can interconvert under the influence of visible light. Certain cells in the retina of our eyes are densely packed with rhodopsin, a large molecule consisting of a protein covalently bonded to cis-retinol. The initial chemical event in vision occurs when rhodopsin absorbs a photon of visible light. The energy of visible photons is sufficient to break the pi bond between carbon-11 and carbon-12. Within a few microseconds after rhodopsin absorbs a photon, the pi bond of retinol breaks, allowing the intact sigma bond between carbon-11 and carbon-12 to rotate. The pi bond then reforms, converting cis-retinol into all-trans retinol. This rapid and substantial change in retinol shape causes the attached protein to change its shape as well, triggering a flow of ions into the retinal cells and initiating electrical impulses, which the optic nerve transmits to the brain. Meanwhile, the free all-trans retinol diffuses away from the protein, is converted back to the cis form, and then rebinds to the protein. Due to the speed and efficiency with which light induces such a large structural change in retinol, evolutionary selection has made this molecule the primary photon absorber in organisms as diverse as purple bacteria, mollusks, insects, and vertebrates, including humans. Hydrocarbons that contain at least one carbon-carbon triple bond are called alkynes, also known as acetylenes. Since alkynes have two fewer hydrogen atoms than alkenes, their general formula is CnH2n-2. The alkyne with 5 carbon atoms has the formula C5H8. A carbon atom involved in a triple bond can bond to only one other atom, so the geometry around each triple bonded carbon is linear. Each carbon is sp hybridized. Finally, due to their localized pi electrons, double and triple bonds between two carbon atoms are electron-rich and act as functional groups. As a result, alkenes and alkynes are much more reactive than alkanes. We will explore this further in the upcoming lectures on important organic transformations and the chemical behavior of functional groups. We should conclude this lecture with a discussion on aromatic compounds. Benzene is a typical example of an aromatic compound. In the benzene molecule, 6 carbon atoms form a hexagonal ring, with one hydrogen atom bonded to each carbon atom. As with carboxylic acids and their conjugate base carboxylates, we need to use the concept of resonance to describe the bonding in molecules like benzene, where alternating double and single bonds are present. We can write two equivalent dominant Lewis structures for benzene, each satisfying the octet rule. Note that the double bonds appear in different locations in the two structures, and each structure depicts 3 carbon-carbon single bonds and 3 carbon-carbon double bonds, which would typically differ in length. However, experimental data show that all 6 carbon-carbon bonds in benzene are equal in length, with a bond length intermediate between that of a typical carbon-carbon single bond and a carbon-carbon double bond. In other words, a more accurate depiction of benzene is as a resonance hybrid, represented by a circle or dashed circle inside the hexagonal ring to illustrate the delocalized nature of the pi electrons. The orbital diagram on the right shows the 2 lobes of the delocalized pi cloud extending above and below the hexagonal plane of the sigma-bonded carbon atoms. This unique bonding arrangement gives benzene special stability. As a result, millions of organic compounds contain the 6-membered benzene ring, many of which are crucial in biochemistry, pharmaceuticals, and the production of modern materials. For aromatic hydrocarbons, we still heavily rely on common names. For example, benzene with a methyl group attached is systematically named methylbenzene, but is better known by its common name, toluene. Benzene with a hydroxyl group is called phenol, while benzene with an amino group is known as aniline, etc. To sum up, in this and previous lectures, you have been introduced to hydrocarbons. We started with alkanes, where carbon atoms are bonded together only by single bonds. In alkanes, Each carbon is tetrahedral and has bond angles of approximately 109 degrees. Hydrocarbons possessing at least one carbon-carbon double bond are called alkenes or olefins. The carbon atoms involved in the double bond have a trigonal planar geometry with bond angles close to 120 degrees. If the carbons in the double bond have different substituents, alkenes can exist as two geometric isomers, commonly denoted as cis and trans isomers. Molecules with multiple double bonds play an important role in fission. Hydrocarbons containing at least one carbon-carbon triple bond are called alkynes or acetylenes. Both alkenes and alkynes are unsaturated hydrocarbons because the carbon atoms in double and triple bonds have fewer hydrogen atoms than those in alkanes. Finally, we briefly discussed aromatic hydrocarbons, whose bonding can only be explained using the concept of resonance. Aromatic hydrocarbons like benzene are flat, cyclic systems with delocalized pi electrons, which enhance their stability. In the following lectures, we will begin examining the most common chemical transformations typical for organic compounds. Thank you for your attention. Hello, everyone, and welcome back to the lecture series introducing you to the basic principles of organic chemistry. In the module on chemical transformations in aqueous solutions, you have learned about the main groups of reactions typical for inorganic compounds. Here, my aim is to introduce you to organic reactions. Before we move forward, I need to clarify some general conventions regarding organic reactions. To depict organic transformations more generally, it is common practice to use the symbol R to represent a non-reacting organic group attached to a reacting atom. You can typically think of R as an alkyl group, a saturated hydrocarbon chain with one available bond. For example, in the generalized depiction of an alkyl bromide shown here, we have an alkyl group attached to a CH2 group bonded to a bromine atom. Similarly, we can depict olefins in a generalized form, as shown here, where R represents an alkyl group attached to one of the carbons in the double bond. The three main types of organic transformations we will discuss in this lecture are addition, elimination, and substitution reactions. These reactions can be easily identified by comparing the number of bonds to carbon in the reactants and products. We will first briefly examine specific examples of these reactions and then extend our discussion to redox reactions involving organic compounds. An addition reaction occurs when an unsaturated reactant becomes a saturated product. Thus, carbon-carbon double and triple bonds, as well as the carbon-oxygen double bond in carbonyl compounds, commonly undergo addition reactions. As a result, the pi bond breaks, leaving the sigma bond intact. In the product, the two carbon atoms form two additional sigma bonds. In the case of carbonyl compounds, these two additional sigma bonds are formed with the carbon and oxygen atoms. Reagents commonly added to multiple bonds include hydrogen gas, halogens, strong acids such as hydrobromic acid, and sometimes water. Finally, the carbon atoms are bonded to more atoms in the product than in the reactant, which is a key characteristic of an addition reaction. As a specific example, we can consider the reaction between ethene and hydrochloric acid, which leads to the formation of chloroethane. Another example is the addition of hydrogen to the double bond in ethene, a process called hydrogenation. In industry, a similar hydrogenation reaction is used to convert unsaturated vegetable oils into saturated fats. Additionally, the addition of bromine to alkenes serves as the basis for a well-known color test for the presence of carbon-carbon double bonds, a method that is still widely used today. In the experiment shown, the test tube on the left contains a compound with no carbon-carbon double bonds, so the bromine does not react and retains its characteristic brown color. In contrast, the test tube on the right contains a compound with a double bond, which reacts with bromine, causing its orange-brown color to disappear. Elimination reactions are the opposite of addition reactions. They occur when a saturated reactant becomes an unsaturated product. In the case of eliminations, two sigma bonds are broken and replaced by a pi bond between two carbon atoms. Typical groups that undergo elimination include a pair of halogen atoms, a hydrogen atom and a halogen atom, or a hydrogen atom and a hydroxyl group. Also, keep in mind that carbon atoms themselves do not undergo elimination. Finally, in these transformations, the carbon atoms are bonded to fewer atoms in the product than in the reactant, which is a key characteristic of an elimination reaction. For instance, here you see a typical elimination reaction where an alcohol is converted into an olefin. A hydrogen atom and a hydroxyl group are eliminated in the form of water, and this type of reaction is typically catalyzed by a strong acid, which is why you see sulfuric acid on the reaction arrow. A substitution reaction occurs when an atom, or a group, in one reactant replaces a group attached to a carbon in the other reactant. In substitution reactions, the carbon atom carrying the leaving group may be either saturated or unsaturated. In these reactions, a sigma bond is broken, and a new sigma bond is formed. The leaving group or the atoms that are eliminated can vary, but they are generally not carbon. Finally, in these reactions, the carbon atom is bonded to the same number of atoms in both the product and the reactant. This characteristic can help you identify whether a given organic transformation is a substitution reaction. As an example, here you can see the synthesis of the main flavor ingredient in banana oil, where a chlorine atom attached to a carbonyl group is replaced by an oxygen atom from an alcohol. Oxidation reduction is an important process in many organic reactions. Even though a redox reaction always involves both oxidation and reduction, organic chemists typically focus only on the organic reactant. Instead of tracking changes in the oxidation numbers of carbon atoms, they usually observe the movement of electron density around a carbon atom by counting the number of bonds to more electronegative atoms, such as oxygen, or less electronegative atoms, such as hydrogen. A more electronegative atom withdraws electron density from carbon, whereas a less electronegative atom donates electron density to it. Therefore, when a carbon atom in the organic reactant forms more bonds to oxygen or fewer bonds to hydrogen, thus losing electron density, the reactant is oxidized, and the reaction is called an oxidation. Conversely, when a carbon atom forms fewer bonds to oxygen or more bonds to hydrogen, thus gaining electron density, the reactant is reduced, and the reaction is called a reduction. The most dramatic redox reactions are combustion reactions. Virtually all organic compounds contain carbon and hydrogen atoms and burn in excess oxygen to form carbon dioxide and water. For the combustion of ethane, the reaction is presented here. Clearly, when ethane is converted to CO2 and water, each of its carbon atoms forms more bonds to oxygen and fewer bonds to hydrogen. Thus, ethane is oxidized, and this reaction is referred to as an oxidation, even though oxygen is reduced to form water during combustion. Most oxidations do not involve the complete breakdown of the molecule, as is the case in combustion. For instance, when 2-propanol reacts with potassium dichromate in acidic solution, it forms 2-propanone, commonly known as acetone. Here, the mixture of potassium dichromate in acidic solution is a common oxidizing agent in organic reactions. Note that in the product, the carbon bound to oxygen has one fewer bond to hydrogen and one more bond to oxygen than in the starting alcohol. In other words, 2-propanol is oxidized, making this an oxidation reaction. However, don't forget that the dichromate ion is reduced at the same time. Finally, the reaction between hydrogen gas and an alkene is both an addition and a reduction. In this reaction scheme, we see that each carbon in ethane has more bonds to hydrogen than in ethene, meaning that ethene is reduced. The hydrogen gas is oxidized in the process, and the palladium shown above the arrow acts as a catalyst to speed up the reaction. The majority of reactions typical for alkanes can be considered oxidation processes, as they are accompanied by either the loss of hydrogen atoms or the replacement of hydrogen with electronegative heteroatoms. Since alkanes are relatively inert molecules, most of their reactions occur through the formation of free radicals, either by the scission of a carbon-carbon bond or by hydrogen abstraction. You may have heard of free radicals, which gain their reactivity from having an unpaired electron. Halogenation of alkanes is a typical example of a redox reaction involving free radicals. When we treat methane with chlorine in the dark, nothing happens. However, as soon as we turn on the light, the two reagents react violently, generating a mixture of chlorinated hydrocarbons. This reaction follows a radical chain mechanism involving 3 steps: initiation, propagation, and termination. The initiation step produces the first radicals. In this example, the absorption of light by chlorine causes the homolytic cleavage of the chlorine-chlorine bond, leading to the formation of 2 chlorine radicals. Next, we have the propagation steps, where the newly formed radicals collide with other molecules, generating new radicals. In our example, a chlorine radical can remove a hydrogen atom from a methane molecule. This step produces a stable product, hydrogen chloride, and an unstable methyl radical, which is highly reactive because its carbon has only 7 valence electrons. When a molecule of chlorine encounters the methyl radical, 1 chlorine atom is transferred to the carbon, forming a stable molecule of chloromethane. The second chlorine atom, formed in this process, can react with another methane molecule, continuing the propagation cycle. The termination step occurs when 2 radicals combine to form an unreactive product. For example, 2 methyl radicals can combine to form ethane, or a methyl radical can combine with a chlorine atom to form chloromethane. In chloromethane, the carbon is bound to electronegative chlorine and has fewer hydrogen atoms than the starting methane, meaning that methane has been oxidized. Free radical chain reactions also occur in biological systems, where harmful radicals attack functional and structural molecules within cells, leading to dysfunction or cell death. Natural antioxidants protect our cells by reacting with free radicals and terminating the propagation of radical reactions. An antioxidant is a compound that prevents an oxidation reaction from occurring. Naturally occurring antioxidants include vitamin E, vitamin C, and flavonoids. There are also many synthetic antioxidants, such as butylated hydroxytoluene, commonly abbreviated as BHD. Synthetic antioxidants are added to packaged and processed foods to prevent oxidation and spoilage. Vitamin E and BHD are radical inhibitors, meaning they terminate radical chain mechanisms by reacting with radicals. At this point, you may rightfully ask, how do they trap radicals? Well, both vitamin E and BHD are derivatives of the aromatic compound phenol, and they use the hydroxyl group bonded to the benzene ring to trap radicals. If we represent a generalized radical as R with a dot symbolizing the unpaired electron, we can depict the neutralization of the radical as shown here. Radicals abstract a hydrogen atom from the hydroxyl group of the antioxidant, generating an oxygen center radical. Systems like this are quite stable because the unpaired electron can be delocalized over many atoms via resonance, as illustrated on the right. Because of this enhanced stability, the newly formed radical does not participate in chain propagation reactions, but instead terminates the chain and stops the oxidation process. All phenols, including vitamin E and BHD, inhibit oxidation through this radical process. The many nonpolar carbon-carbon and carbon-hydrogen bonds of vitamin E make it fat-soluble, allowing it to dissolve in the nonpolar interior of the cell membrane, where it is thought to inhibit the oxidation of unsaturated fatty acid residues in phospholipids. Oxidative damage to cellular lipids via radical mechanisms is believed to play a significant role in the aging process. For this reason, many anti-aging formulas containing antioxidants like vitamin E are now popular consumer products. To sum up, in this lecture, we discussed the main types of organic transformations. You saw that in an addition reaction, a pi bond breaks, and the two carbon atoms become bonded to more atoms in the product. You also learned about elimination reactions, where a pi bond forms, and the two carbon atoms end up bonded to fewer atoms in the product. Then, we discussed substitution reactions, in which one atom bonded to carbon is replaced by another, while the total number of atoms bonded to the carbon remains unchanged. Finally, we examined organic redox reactions, where the organic reactant is oxidized if at least one of its carbon atoms forms more bonds to oxygen or another electronegative element. Conversely, in a reduction reaction, a carbon atom in an organic molecule forms more bonds to hydrogen. In the concluding lecture of this module, I will introduce you to the most important functional groups found in organic molecules, and we will discuss their key properties. Thank you for your attention. Hello, everyone, and welcome to the concluding lecture in our series on organic chemistry. The vast variety in organic chemistry arises from the numerous ways carbon chains and rings can be constructed and the diverse selection of functional groups that can be attached to them. Functional groups determine the reactivity and function of organic molecules and are given special attention, much like an ace in a card game. In general, a site of reactivity in an organic molecule is called a functional group because it typically controls how the molecule behaves or functions under specific conditions. Functional groups define both the reactivity and classification of organic molecules. As you will soon see, the presence of carbon-carbon double or triple bonds in a hydrocarbon significantly increases the compound's reactivity. Furthermore, these two functional groups undergo similar, yet characteristic reactions. The same principle applies to other functional groups. Each distinct type of functional group often undergoes similar reactions, regardless of the molecule's size and complexity. Functional groups are commonly classified by bond order, as this classification reflects their patterns of reactivity. For instance, functional groups with only single bonds typically undergo elimination or substitution reactions, while those with double or triple bonds are prone to addition reactions. Functional groups containing both single and double bonds usually undergo substitution reactions. In this lecture, we will examine the properties of common functional groups and summarize their typical reactions. The most common functional groups containing only single bonds are alcohols, haloalkanes, and amines. The alcohol functional group consists of a carbon atom bonded to a hydroxyl group, and it is generally represented as RH. Alcohols are named by replacing the ending E of the parent hydrocarbon with the suffix OL. For example, the 2-carbon alcohol is ethanol, while a 5-carbon alcohol is pentanol. The most well-known alcohol is ethanol, which is commonly obtained from fermented grain and has been consumed as an intoxicant in beverages since ancient times. Today, it is recognized as the most widely abused drug in the world. Alcohols are common organic reactants, and the hydroxyl functional group is found in many biomolecules, including carbohydrates, sterols, and certain amino acids. Below, you can see the names, structures, and applications of some important compounds that contain a hydroxyl group attached to a hydrocarbon skeleton. The physical properties of smaller alcohols are similar to those of water. They have high melting and boiling points due to hydrogen bonding and can dissolve polar molecules and some salts. As you may have already guessed, alcohols undergo both elimination and substitution reactions. In an elimination reaction, the removal of a hydrogen atom and a hydroxyl group, known as dehydration, produces an alkene. This reaction requires an acid catalyst. The elimination of two hydrogen atoms is an oxidation reaction that requires an inorganic oxidizing agent, such as potassium dichromate in aqueous sulfuric acid. This oxidative elimination results in the formation of a carbonyl-containing compound, typically a ketone. Interestingly, alcohols with a hydroxyl group at the end of the hydrocarbon chain can be further oxidized to carboxylic acids. In this case, the final step is not an elimination reaction. This oxidation process explains why wine turns sour when exposed to air for long periods. Finally, alcohols also participate in substitution reactions, producing compounds with other single-bonded functional groups. When alcohols react with hydrohalic acids, they form haloalkanes, as shown in this generalized reaction scheme. In a substitution reaction like this one, the carbon atom undergoing transformation is bonded to a more electronegative element, making it partially positive and, therefore, a target for an incoming negatively charged or electron-rich group. A halogen atom bonded to a carbon forms the haloalkane functional group, typically represented by the general formula Rx, where R corresponds to a hydrocarbon framework and X denotes a halogen atom. Like alcohols, haloalkanes undergo both substitution and elimination reactions. Just as many alcohols undergo substitution to form alkyl halides when treated with halide ions and acid, many haloalkanes undergo substitution in base to form alcohols. For example, as it is shown below, a hydroxide ion can attack the carbon end of the carbon-halogen bond and displaces the halide ion. Similar substitution reactions involving nucleophiles such as cyanide, thiols, alkoxides, and amines allow chemists to convert haloalkanes into a wide variety of other compounds. Finally, just as the addition of hydrogen chloride to an alkene produces a chloroalkane, the elimination of hydrogen chloride from a chloroalkane, when reacted with a strong base, such as potassium ethoxide, yields an alkene. The enhanced reactivity of haloalkanes makes them active mutagens. Some halogenated aromatic hydrocarbons are carcinogenic in mammals, have severe neurological effects in humans, and, to make matters worse, are highly stable in the environment. For example, polychlorinated biphenyls, which are used as insulating fluids in electrical transformers, have accumulated in rivers and lakes for decades and have entered the food chain. As a result, the presence of polychlorinated biphenyls in natural waters poses significant health risks and presents a major environmental cleanup challenge. An amine is a derivative of ammonia in which one, two, or all three hydrogen atoms are replaced by hydrocarbon groups. When only one hydrocarbon framework is connected to the nitrogen, the compound is a primary amine. Two alkyl chains make the amine secondary, whereas in tertiary amines, the nitrogen is bonded to three organic substituents. Note that the R groups in secondary and tertiary amines can be the same or different. Like ammonia, amines have a trigonal pyramidal shape with a lone pair of electrons on a partially negative nitrogen atom, which plays a key role in amine reactivity. The amine functional group is widespread in many natural products, including, but not limited to, amino acids, alkaloids, and nucleic bases. The amino group is also common in biologically active molecules such as epinephrine, adrenaline, and cocaine. primary and secondary amines can form hydrogen bonds, giving them higher melting and boiling points than hydrocarbons and alkyl halides of similar molar mass. For example, dimethylamine boils 45 degrees higher than ethyl fluoride, despite their similar molecular masses. On the other hand, trimethylamine has a greater molar mass than dimethylamine, yet it melts more than 20 degrees lower because it lacks hydrogen atoms bound to nitrogen that could participate in hydrogen bonding. Low molar mass amines have a fishy odor, are water-soluble, and are weakly basic due to the lone pair on nitrogen. For instance, the reaction of amines with water proceeds only slightly to the right before reaching equilibrium. This lone pair also enables amines to undergo substitution reactions. Amines use their lone pair of electrons to attack the partially positive carbon in an alkyl halide, displacing the halide ion and forming a larger amine. Note that this reaction requires two molecules of amine. One attacks the chloroethane, while the other binds to the released hydrogen ion, preventing it from remaining on the diethylamine product. The most important functional groups with double bonds are the carbon-carbon double bonds in alkenes and the carbonyl groups in aldehydes and ketones. Both are present in many organic and biological molecules. The most common reaction type for functional groups with double bonds is addition. Alkenes undergo various electrophilic addition reactions. Their electron-rich double bond is readily attracted to the partially positive hydrogen atoms in hydronium ions and hydrohalic acids, leading to the formation of alcohols and alkyl halides, respectively. The addition of halogens and hydrogen to alkenes was discussed in the previous lecture. Here, it is worth mentioning that alkenes can also undergo radical addition reactions, which lead to polymerization. However, this is a separate topic that will be covered in the lectures on synthetic addition polymers. We should also have a brief discussion about the reactivity of aromatic compounds. The localized unsaturation of alkenes is very different from the delocalized unsaturation of aromatic compounds. That is, despite how we depict its resonance forms, benzene does not have discrete double bonds. For example, without the addition of special catalysts, it does not decolorize bromine as alkenes do. In general, aromatic rings are much less reactive than alkenes because of their delocalized pi electrons. For instance, let's compare the reaction energies for hydrogen addition. Hydrogenation of cyclohexene, which contains one carbon-carbon double bond, releases 120 kilojoules of energy per mole of substrate. For the hypothetical molecule cyclohexatrine, which have three localized carbon-carbon double bonds, the expected energy release from hydrogenation would be 3 times as much, or 360 kilojoules per mole. However, experiments show that hydrogenation of 1 mole of benzene releases only 208 kilojoules of energy. This means the energy required to hydrogenate benzene is 152 kilojoules less than that for the hypothetical molecule with 3 localized double bonds. This energy difference is attributed to the aromatic resonance stabilization of benzene. The extra energy needed to break up the delocalized pi system means that benzene rarely undergoes addition reactions. However, benzene readily undergoes many substitution reactions, where delocalization is preserved when a hydrogen atom attached to a ring carbon is replaced by another group. This is demonstrated here with the Lewis acid-catalyzed bromination of benzene. The carbon-oxygen double bond, also called the carbonyl group, is one of the most versatile functional groups in nature, pharmacy, and organic chemistry. In aldehydes, the carbonyl carbon is bonded to a hydrogen atom and typically to another carbon atom, meaning it occurs at the end of a hydrocarbon chain. This can be represented by the general formula shown on the left. On the other hand, in ketones, the carbonyl carbon is bonded to two other carbon atoms, meaning it occurs within a hydrocarbon chain. Ketones can be represented by the general formula shown on the right. Some important carbonyl compounds are presented here. Try to memorize their names and structures, as you may encounter them later in the course. You probably remember from our discussion on the properties of alcohols that aldehydes are formed by the oxidation of primary alcohols, whereas ketones can be synthesized by the oxidation of secondary alcohols. Conversely, due to their unsaturation, carbonyl compounds can undergo many addition reactions. When we use hydrogen or another reducing agent in an addition reaction, carbonyl compounds can be reduced to their corresponding alcohols. Like the carbon-carbon double bond, the carbon-oxygen bond is electron-rich. However, unlike the carbon-carbon double bond, the carbonyl group is highly polar and has a strong dipole moment. Due to this bond polarity, addition often occurs with an electron-rich group bonding to the carbonyl carbon and an electron-poor group bonding to the carbonyl oxygen. The polarization of the carbonyl group is so strong that even weak nucleophiles, such as water, alcohols, and amines, can attack it using their lone pairs of electrons. The nucleophilic addition reaction involving alcohols is presented here. When only one molecule of alcohol adds to the carbonyl group, the product is called a hemiacetal. These reactions work particularly well in the presence of acid catalysts, which can facilitate a follow-up nucleophilic substitution of the hydroxyl group in the hemiacetal with another molecule of alcohol. The product formed in this case is known as an acetal. In the end, we should briefly discuss a family of three functional groups that contain a carbon atom double bonded to oxygen and single bonded to either oxygen or nitrogen. The parent of this family is carboxylic acid, which contains the functional group commonly called the carboxyl group. A general representation of carboxylic acids is shown on the left. Other important derivatives of carboxylic acids include esters and amides. The most important reaction type in this family is substitution, allowing the conversion of one member into another. For instance, substitution of the hydroxyl group with the alkoxide of an alcohol forms an ester, while substitution of the hydroxyl group with the nitrogen of an amine forms an amide. Here, we will only focus on the chemistry of carboxylic acids. The chemical behavior and properties of esters and amides will be examined in the lectures on lipids and proteins, respectively. Carboxylic acids are widespread in nature, and some important representatives, along with their names and properties, are presented here. Formic acid, for example, is the irritating component of ant and bee stings. Benzoic acid is used as a food preservative, and you probably consume significant amounts of this substance on a daily basis. In the carboxyl group, highlighted in these molecules in pink, the carbon already has 3 bonds, so it can form only one additional bond, either to a hydrocarbon skeleton, as in benzoic acid or butyric acid, or to a hydrogen atom, as in formic acid. Carboxylic acids with long hydrocarbon chains are known as fatty acids, an essential group of compounds found in all cells. Animal fatty acids typically have saturated chains, whereas many plant-derived fatty acids are unsaturated, usually with carbon-carbon double bonds in the cis configuration. These double bonds make them much easier to metabolize. Nearly all fatty acid skeletons contain an even number of carbon atoms because cells use 2 carbon units in their synthesis. You may recall that carboxylic acids are weak acids when dissolved in water. At equilibrium in a solution of typical concentration, more than 99% of the acid molecules remain undissociated at any given moment. However, in a strong base, a carboxylic acid reacts completely to form a salt and water. The salts of carboxylic acids are good electrolytes and dissociate completely in water. Substitution reactions of carboxylic acids and other members of this family occur through a two-step sequence. Addition followed by elimination, which results in an overall substitution. Addition to the trigonal planar carbon atom gives an unstable tetrahedral intermediate, which immediately undergoes elimination to revert to a trigonal planar product. For instance, strong heating of carboxylic acid leads to the formation of an acid anhydride through a type of substitution called a dehydration condensation reaction. Viewing this reaction as similar to the one previously discussed, we see that the result is the condensation of two acid molecules into one, with the loss of a water molecule. To sum up, in this lecture, you have learned about the most important chemical transformations characteristic of the common functional groups found in organic compounds. Organic reactions are initiated when regions of high and low electron density in reactant molecules attract each other. Functional groups containing only single bonds, such as alcohols, haloalkanes, and amines, undergo substitution and elimination reactions. Functional groups with double bonds, such as alkenes, aldehydes, and ketones, primarily undergo addition reactions. You also learned that aromatic compounds are generally unreactive. Despite having carbon-carbon double bonds, they typically undergo substitution rather than addition and do so only in the presence of special catalysts. Finally, we discussed functional groups containing both double and single bonds, with a primary focus on carboxylic acids. Carboxylic acids, esters, and amides can interconvert by substitution reactions at the carbonyl group. In the next module, we will continue our discussion by focusing on the properties of amides and esters. You will also be introduced to natural and synthetic macromolecules. Thank you for your attention and participation.